All right, let's talk about the first order reactions. All right, so a typical example of a first order reaction is the decomposition of hydrogen peroxide into oxygen and water. All right, so if the reaction is truly first order, what that means is that the rate law, negative k times a to the n, is really going to have to equal negative k times a to the first power, meaning that the rate is equal to negative k times the concentration of A. And so what this actually tells you is that the reaction rate is going to be changing as time goes by, because as the reaction progresses forward, the concentration of this reactant is going to start decreasing, in other words, changing. And as the concentration changes, so will the rate, because now the rate does depend on the concentration of the reactant. All right, now, same idea as we did before. If we treat this using calculus, we know that the rate is the change in concentration of A over the change in time. But this time, this is going to equal negative K times the concentration of A. So what we do from the point of view of calculus is to bring all the variables of the same kind to the same side, and the variables of the different kind to the opposite side. And by that, what I mean is that we're going to cross multiply dt and the concentration of A to end up with the following: dA over A equals negative k dt. If you take the integral of both sides, going from the initial concentration to the final concentration at time 0 up to some time later, what you're going to end up yielding, and by the way, the negative k is a constant, so in calculus, constants can be taken out of the integral to simply multiply the integral itself. And so whatever happens in terms of this integral, you just multiply by negative k, and that's the resulting value. Now, when you have something like this, right? This is technically something like dx over x or 1 over x dx. The integral of such a function is the natural log of that parameter. Now, this has ultimately proofs in calculus that you can go through and that you can actually convince yourself that yes, in fact, this integral is the natural log. But that is way beyond what I care to talk about in this class. In fact, as is, showing you the integrals may actually be, putting off some of you just because you may have not taken calculus. But I think it's kind of important to see the correlations here. There's actually an application of calculus, very much so, as you can see in this slide, within chemistry. And it's not the only time that calculus makes an appearance. All right, so once again, the natural log of the final state minus the natural log of the initial state. So we get for the left side of this equation, on the right side we have negative k times time t minus 0, which is the same thing as natural log of A minus natural log of the initial concentration of A equaling negative kt. So if you move the natural log of A naught to the right side of the equation, we end up yet with another linear equation, one in which the y value of the y equals mx plus b equation is the ln of the concentration, and the x value is the time. So what this is telling you is that if you plot concentration versus time, you will not get a linear plot out of this first order reaction. But if instead you take the natural log of the concentration and plot those values versus time, that will give you a linear plot with a negative slope. And once again, the negative slope of that line is equal to the rate constant. So that's what this integrated rate law is telling you. Another way in which you can see this equation comes in the form of the combination of logs, because the ln of A minus the ln of A naught can be put together as the natural log of final concentration over initial. Remember that subtracting logs is the same thing as dividing the insides of the logs, right? So this is another way in which the integrated rate law can, be depicted, shown, or utilized. In some cases, you want to stick to the upper, format of the integrated rate law, or you might want to use the one right here. Okay, and this is kind of like the two-point equation because you have concentrations. You can use that to find the value of K at some time. But, it just depends on the case. So, once again, if you have the data, if you have the concentration versus time data, if you plot concentration versus time, what you're going to find out is that this doesn't give you a line. Sometimes it may look like a line, but if you look at the correlation value, you're going to find out the correlation is actually not very good. Anything that's below 0.98, it's already pretty bad in terms of having a linear correlation. So negative 0.95, yeah, definitely not linear. And you can see that very clearly. That has more of a curve um, shape to it, an exponential shape to it. All right, so if we actually take the ln of the concentrations, and I would recommend that you do that using Excel, Logger Pro, or some other program to save you some time, you will end up getting the following values. Now, plotting the natural log of A, which is basically all the negative values that you see here, versus time, it shows you a graph for which you have a very linearly looking, linear looking graph. The correlation value, in fact, is exact for this, for this example. Okay, so this is as good as it gets, right? This is, in fact, um, a first order reaction. And the fact that this is linear when you plot ln of A versus time is the proof that you need in order to tell that this is a first order reaction. Because what you got to remember is that when you do experiments, you don't know the order of the reaction to begin with. You're doing the experiment to derive the order. And so if plotting concentration versus time gives you the best line, then this is telling you this is a zeroth order reaction. On the other hand, if you plot the ln of A versus time and you get a linear plot or the best linear plot, then you're dealing with a first order reaction. And as you'll find out in a little bit, if you plot the inverse of the concentration versus time and you get a linear or the best linear plot, then you're dealing with a second order equation. But in any of these cases, the slope is always the same thing. The slope represents the rate constant. So that's the other reason why we do that. Not only do we get the order, but we get the value of the rate constant as well, which now you're kind of beginning to see the trend. You do this type of experiments, concentrations versus time experiments, to find out what order you're dealing with and find out the rate constant. And if you vary the temperatures and redo the experiment again at different temperatures, you will end up getting the rate constants at different temperatures. And with that data, you can actually find out the activation energy of the reaction itself. So I think hopefully you're beginning to see the snowballing effect of all of this stuff. All right, so as I was telling you, this is a linear plot when you plot ln of A versus time, telling you that this is a first order reaction. And the rate constant is 1.06 times 10 to the negative 3, quite literally the positive value of the slope of this line. All right, so I'm just writing it there in standard notation. And if you want to calculate the rate for a first order reaction, right, so that's where the ln of A versus time plot is going to come in handy, because that will tell you this is a first order reaction. So now you know that the initial rate has to be given by negative k multiplied by the initial concentration of A. All right, so the initial concentration is the one at time 0, which according to the graph is 0.02. Don't make the mistake of using negative 3.912. That's the ln of A, that's not the initial concentration, that's the ln of the initial concentration, not the same thing. This has to be exclusively just the initial concentration. So if you multiply negative 0.00106 by 0.02 molar, you're going to end up with the concentration in molar per second. And once again, man, I gotta change the slides. This is in minutes, right? Because the time is in minutes, so this is actually molarity per minute. Okay, so the actual concentration or the rate is going to depend in terms of what the time is. So if the time is in minutes, the rate is in minutes. If the time is in seconds, the rate is in seconds. All right, but the molarity is going to be constant every time that you're dealing with rates. All right, now generally speaking, that procedure that is presented to you is what you will do if you have a computer and a computer program to perform the task. But if you're being asked to do this on paper, which may not be the situation at hand, but if you're asked to be doing this on paper, then you basically have no choice but to calculate the slopes manually for each one of these columns. So specifically, the slope of concentration versus time. So you pick two data points within concentration versus time, see what you get, and then you pick two other data points and see what you get. You might even do that for a third data point. And the idea is that if the value that you selected for the y versus time is indeed linear, the slope ought to be the same for every calculation that you're performing. If it keeps changing and changing a lot, then that tells you the plot is not linear and that's not the order of the reaction. So you move on to the next thing, which will be the ln of a, and then perform the slope calculation. So to give you an idea, I'm using negative 4.135 minus negative 3.912, which is what you see here on top, and the time difference is 200 minus 0, which gives us a slope of negative 0.00112. If I pick the next set of rows, right, so for negative 4.335 minus negative 4.135, which is what I have on top, on the bottom I divide by 400 minus 200, and I get a value that is kind of close to this one. And then if you average out the values, by the way, so add them together, divide them by 2, you actually get the value that we got originally here. So the idea that I'm trying to portray here is that if you have the option to use Excel to do this type of problems, then use Excel. Only if you're doing this by hand, like an exam on paper, where you are not allowed to use a computer, then you will have to do this manually the way I'm presenting right here. But any other situation where the computer is available to you to be used, use the computer, use Excel to perform, to basically graph concentration versus time, ln of concentration versus time, find out which one is the most linear plot. All right, let's talk now about the second order reactions to finish this up. Second order reactions are those in which the exponent in the rate law is equal to 2. All right, so the rate is equal to negative k times the square concentration. Using calculus, once again, you have dA over dt equaling negative k times concentration square. Separating the variables, so dividing by the concentration square and multiplying by dt gives you the following relationship. Taking the integrals of both sides tells you that, yeah, I'm bringing the constant outside of the integral. Basically tells you that for the case where you have 1 over a squared, the integral is negative 1 over a. And so you have negative 1 over a final minus negative 1 over a initial, and that equals negative k times time minus 0, which ultimately means that negative 1 over a final plus 1 over a initial equals negative kt. And if we rearrange this such that 1 over a final is positive, then pretty much what we do is multiply everything by negative 1 in this equation, right? And so now we have a relationship for which 1 over the concentration gives you, versus time, gives you a linear plot, a plot that actually has a positive slope, okay? So 1 over concentration versus time, if this provides you with a line or the graph with the best line, that tells you that the reaction is second order. And once again, if you have the data table, right, concentration versus time, and you plot concentration versus time, you see this is a crap equation, right? This is the correlation is just like total crap, right? This is not even close to being linear. You can then take a look at the ln of a, take the ln of a, and then plot ln of a versus time. And if that doesn't give you a line, then you take the inverse of a, not the inverse of ln of a, but the inverse of a, and plot that versus time. And if that gives you the best line, which in this case, that tends to be the case, right? You have a correlation of 1 when we plot 1 over a versus time. That significance tells us that, or that relationship tells us that we are dealing with a second order reaction. And what that also tells us is that the rate constant ought to equal 8.5 times 10 to the negative 3. Literally the slope of the line, of the best line. All right, so using that, we can also calculate the initial rate. The initial rate is simply negative k times the initial concentration square for a second order reaction. So we multiply 0.0085 by the initial concentration, which was 8, but we squared that. So we're going to end up with 0.544 molar, and once again, this should be per minute, not per second. But as you can see, finding the best line relationship upon plotting concentration versus time, or ln of A versus time, or 1 over concentration versus time, is the means by which we find out which order we're dealing with. Also the means by which we determine which rate constant we're actually going to use, and also the means by which we can find out the initial rate of the reaction. Alright, so in the next video, I am going to tell you how to calculate and derive something known as the half-lives, which tell you a little bit about how long it takes for a reaction to go halfway. But I'll start talking about that on the next video, so see you then.